La 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 la. Okay. I will begin with a word of prayer. Heavenly Father, we thank you again for this time we have to meet together and study calculus. I just pray that you'd bless this class, Lord. In your name I pray. Amen. Well, anyway, I hope you guys are starting to get the idea of how to calculate limits of sequences. There is still time to fix what you don't understand, but I hope you got something out of that quiz. So improper integration, there's really a couple different kinds of improper integration we have to talk about. The one is something like this. The integral from, say, some constant a to infinity of f of x dx. Well, this is defined to be the limit as, let's say, b goes to infinity of the integral from a to b of f of x dx. So we just define it in terms of the limit of the bound going to infinity. Likewise, the integral from, say, minus infinity to a of f of x dx, let's say, well, fine, a, yeah, is equal to the limit, and you can use whatever letter you want. I'll use t this time. T goes to minus infinity of the integral from t to a of f of x dx. All right. If you have both infinity and minus infinity in the integral, like so, then you got choices. Whatever. You can say integral from minus infinity to, say, 0. But you can put anything you want here. Let's just say a. All right? You can choose a equals to 0 or 1, whatever. Whatever you want. The point is that those are separate infinities. So that explicitly involves two separate limits. Okay? Now, I'm assuming in these that I'm assuming that f is piecewise. I can't spell piecewise. Piecewise continuous on either a to infinity or minus infinity to a, or in the last one, minus infinity to infinity. These are what's assumed when I make these definitions, all right? Let me give you an example of each. The integral from 0 to infinity of dx over 1 plus x squared is the limit as, let's say, b goes to infinity of the integral from 0 to b of dx over 1 plus x squared. But what's that? So that's inverse tangent, right, of b minus inverse tangent of 0 by the fundamental theorem of calculus part 2. Of course, inverse tangent of 0, you know it, you love it. It's 0. So that's 0. And what's the limit as b goes to infinity of inverse tangent b? I hope by now you're starting to be familiar with the fact that that's pi over 2. Right? So there you have it. Did I do this example last time? I can't remember. I have a vague, I don't remember which one I did. Similarly, any questions about that before I show you another example? Let me call that example 1. I'll call this example 2, whatever I'm about to do. So what if I was going to integrate, say, from minus infinity to 0 e to the x dx? Okay, so this would be the limit as t goes to minus infinity of the integral from t to 0 of e to the x dx. We can do that integral without a lot of work, right? So we have limit t goes to minus infinity of what? Of e to the 0 minus e to the t. e to the 0, you know it, you love it. It's 1, yes. And what happens to e to the t as t goes to minus infinity? Yeah, that goes to 0. So in total, we get 1. So it's pretty interesting results that I'm coming across here right now. What we just proved, this 1 over 1 plus x squared looks something like this, right? E to the x is this guy, right? And what we just proved for this one, we proved this area right here. That area is pi over 2. Goes on and on and on. And we just proved this area right here, right, has area 1. Right? Of course, if you keep going, the exponential does what? Like that, right? So if I were to calculate the integral from 0 to infinity for the exponential, I would get what? Yeah, that would work out to infinity, right? All right, example 3. How about the integral from minus infinity to infinity, all right, of, let's see here, how about sine of x dx? Okay, check this out. So the limit as t goes to infinity, right, the integral from minus t to t, sine of x dx. So that's the limit as t goes to infinity of what? Of, looks like a cosine, well, minus cosine of t, right? Plus cosine of minus t. Oh, but what's that? Zero, right? So the answer is 0, right? Definitions matter, right? So I have not followed the definition in this calculation, have I? What's the definition of the doubly infinite integral? It's given over here, right? I'll box it for you. It doesn't say that I use the same limiting process for both bounds. See, in more detail, this is something like the limit as t goes to minus infinity of the integral from, let's just make it 0. 0 to t, f of x dx, right? Plus the limit as b goes to infinity of the integral from a to b of f of x dx. But I think it's important to notice that this right here and this right here, these are separate limiting processes. They're separate limits. They can't be connected. If they're connected, it's not the same thing. See, because this right here, if I split into pieces, I don't get 0, right? Suppose we integrate from minus infinity to 0, sine of x dx plus the integral from 0 to infinity, sine of x dx. Well, then this is the limit as, t goes to minus infinity of, minus cosine of 0 plus cosine t plus the limit as b goes to infinity of like minus cosine of b plus 1. Cosine of 0 if you like. The point is, these diverge. These both diverge due to oscillation at infinity or minus infinity, right? diverges. This also diverges because the cosine never settles down to something. Yep.
Is there a reason that the first limit is t to 0 and then the other one's like a to b, but I understand like t and b.
Oh, that was supposed to be 0.
Oh, okay.
That's supposed to be a 0. Sorry about that. You could put an a in both spots, or you could put a 0 in both spots. You could put a 32. It wouldn't matter. You can listen. The point is, the idea is you've got this function, right? Whatever, and the point is you can split the integral wherever you want it, because we're considering this part and this part separately. We're not doing like my initial calculation is geometrically something like, you're taking this sort of thing and you're just symmetrically expanding it to infinity both ways. That's a different limiting process than the definition. The reason this is 0, right, is because sine is odd. And the integral of any odd function about a symmetric interval of the origin is 0. Right? This is a thing. This is what's called the principal value of the integral from minus infinity to infinity of sine of x dx. That is a thing. It has physical significance. It has significance in the study of signals and systems somewhere. I can't tell you exactly, but I mean that is something that people calculate meaningfully. It means something, all right? But it's not this. So the double integral only exists if the sum of the integral from minus infinity to something plus the integral from something to infinity both separately exist and are finite. Okay? So I include this as just a calculation to warn you that you can't do this. Sorry. But if it's a double integral, if it's an integral from minus infinity to infinity, you gotta do 2 separate ones. I'm sorry, but that's the definition. Now, there are some caveats to that, right? I mean, it is sometimes possible to like double up. Like if I change this to the integral from minus infinity to infinity, because it's an even function, if you get like half of it exists, it follows that the other half also exists. So like without further calculation, I can tell you that the integral, this does imply that the integral from minus infinity to infinity of like dx over 1 plus x squared is equal to pi without further calculation, because there has to be a matching between the left and the right integrals because of the fact the function's even. It's just that when an odd one goes to 0, that doesn't mean that the left and the right halves of an odd function's integral are actually both vanishing, both existing. All right, enough. The other kind of improper integral that I should talk to you guys about is something like this. And let me just illustrate it by example. Let's see here. Where are we? Example 4. I'm going to give you an example before I give you the formal definition, if that's okay. So suppose we're asked to do something like integrate from 0 to 1, all right? 1 over the square root of x dx. See, not every improper integral comes packaged with like these kind are really easy to tell that they're improper, right? It's just like in your face. There's an infinity right there. There's your clue. It's an improper integral, right? This is hard to miss, right? But something like that, it's a little more subtle. This is also an improper integral, but of another sort. See, because, check it out. What do we have here? Square root. Yeah, that's not but the point is, what is the square root of 0? 0, and we have what? Division by 0. See, this function, 1 over f of x equals 1 over the square root of x, is not continuous, or even piecewise continuous, on the closed interval from 0 to 1. I mean, fine, it's continuous on the open interval from 0 to 1, or with 0 not included, but 0 is a problem point, right? And you can't ignore that. So what do we have to, how do we give meaning to something like this? The meaning is the following. So we take the limit, you pick whatever symbol you like. I'm going to use epsilon. Epsilon goes to 0 from the right. The integral from epsilon to 1 of dx over the square root of x. And that's what that's going to mean. So geometrically, this is very satisfying because, like, if you think about what it means, square root 1 to the square root of x is something like, it's got this stupid vertical asymptote right there, right? And what we're saying is to define this integral, we're calculating the integral from, say, epsilon, right, to 1, like this. And then we're just letting epsilon go to 0 from the right. And that should be whatever this limit, and whatever this integral should mean, should be that limit. It may or may not exist, but this is how we define it. All right? It's like, well, how else would you define it? I don't know. I can't think of anything else to do. To me, this is just like, what else would you do? But I guess you still have to make definitions. And so there it is. That's the definition. But I think it's a natural one. So then we do the calculation. What's the integral of 1 over the square root? I think it's twice the square root, right? 2 times the square root of x, and I'll put an in-between step here. I have to evaluate from epsilon to 1. So what's that? That's the limit as epsilon goes to 0 from the right of 2 times the square root of 1 minus 2 times the square root of epsilon. Cool. Even though this has a vertical asymptote, right, the area bounded under that curve from 0 to 1 is finite. In fact, its area is what? It's 2. Yeah. Because this goes to 0, right? Does that make sense? You can mix and match these, all right? You can have combination problems that involve both limits at infinity and hidden improperness. Like I call this a hidden. To me, that's kind of like a hidden improperness. I don't know what the right word is for it. I'm sure your book has a specific title for these. Some books are like type 1 or type 2. I don't know. What's he call it? I forget. I was looking at it 3 minutes ago, but I can't remember. He says, the integral of an unbounded function. That's a pretty good description. So, it's not a bounded function, right? Whoa. It's very exciting. I wonder what's happening. Ooh, new car. We're buying a new car. It's very exciting. Oh, I'm sorry. I know you guys are having trouble concentrating on my lecture today because you're all just like really, really excited about the upcoming vice presidential debate. And I know it's distracting. I'm sorry. I got off my game too today because it's just so exciting.
What kind of car are you getting?
Weasel Face and the other guy. What's that?
What kind of car are you getting?
What kind of car? Oh, a 2000... something 2009 Honda Odyssey, I think. What's that? Yeah, minivan, of course, yeah. I already have my 1996 Toyota Camry, which I will drive into the ground. So I'm sticking with that. It's like, we could buy this van, but I have to be able to drive my car. Let's see here. It's just like, we were floating this idea of getting rid of my Camry so I could drive a minivan to school every day, and I was like, I don't want to park a minivan every day. It just doesn't sound fun. I mean, the minivan does have air conditioning, which is nice, but, my Camry doesn't have air conditioning anymore. And I don't much care because, when a car gets to be a certain age, you just give up on air conditioning. Okay, so how about this? The integral, say from minus infinity to infinity of, I don't know, dx over x minus 2 quantity squared. See, this is this requires some care, because this is like the integral from minus infinity to 2, right? Well, I really need to break this up into pieces. This is like the integral from minus infinity to 1 of dx over x minus 2 quantity squared. I always do an example like this, and then I regret actually writing it out, but I'm going to because it's important for you guys to see it. Integral from 1 to 2 of dx over x minus 2 squared. Now, why am I treating 2 with kid gloves?
Because it makes it a denominator.
Yeah, because 2 is where we have a vertical. Exactly, the function's unbounded at 2. And the 3 and the 1 are totally artificial. I just have to pick something that's beyond 2 and before 2. What's that? I'm doing it because I have no other choice but to do it this way. You know? So there's... So like, this is 1, this is 2, this is 3, this is 4, right? I've defined how to do every one of those kinds of integrals. All right? So this is the limit as, I don't know, t goes to minus infinity. The integral from t to 1 dx over x minus 2 quantity squared plus the limit as, let's say, b goes to 2 from the left, the integral of dx over x minus 2 quantity squared. And that's got bounds that go from b to, from 1 to b. And then plus the limit as, let's say, I don't know, a goes to 2 from the right, the integral from a to 3 of dx over x minus 2 quantity squared, plus the limit as, I don't know, let's use s. I haven't used s yet. S goes to infinity. It doesn't really matter what letter you use, right? Just be, well, anyway. You shouldn't use x. There's pretty much one choice. You can't use x. You know, you got to distinguish between the integration and the limit. There's that, but there it is. Now, what is this integral? What is the integral of dx over x minus 2 quantity squared anyway? I think it's just what, minus 1 over x minus 2? Plus a constant, am I right? I mean, that's the antiderivative, is it not? You guys don't know or you don't care? Don't answer yes. It's not allowed. Let's see here. So we're looking then at the limit as t goes to minus infinity. So this guy gives me, there's a minus here, so I'm going to do lower bound minus upper bound without, you know, it's going to go ahead and take care of the minus by doing the bounds opposite. Yeah, well, here it is. I hope you're wrong, because I've committed to this. So the point is there's a minus here, right? So what I did, rather than writing minus and minus and minus, is I just did the lower minus the upper in each one because, because of this minus here, just to take care of the minus. So this is really upper minus lower, upper minus lower. Wait, did I do that wrong? Let's see if I actually committed to the pattern or not. Oh, here sorry. I got to be consistent, right? Okay, now some of these things cancel, right? For example, this and that are Kaputski, and this guy and that guy, natural enemies. And how about the rest of it?
So you can just...
Well, this piece here goes to 0, right? Well, I don't know if I can do it or not, is the thing. I'm not sure about that. I mean, this is 1. What happens is 2. Oh, this goes to 0, right? So yeah, these guys out here go to 0, but you see the problem is what? This diverges, right? And what about this one? Also diverges, right? See, as b goes to 2 from the left, what do you got? You have a very, very small negative number. So this whole thing blows up to infinity, as does this. So really, these aren't cancel. I mean, I shouldn't really say that this cancels with that. It doesn't cancel. And this doesn't really cancel with the other thing, That limit just blows up, so it's not a cancellation. But anyway, when you got a sum of things, all right, and granted, this is finite. It happens to be equal to 1. This limit's also finite. It happens to be equal to 1, right? All that means geometrically, right, guys, is that, so this thing is like a volcano at 2, right? And so what I've calculated is that the area from 1 to minus infinity, this area right here, is 1. Also the area from 3 to infinity is 1. However, this is infinity, and this is also infinity. In other words, the 2 integral and the 3 integral are both infinite. So in total, the integral diverges. Okay, so we should do an example like this, but yes, it is a pain. So anyway, that's a good start for us. Yeah.
You said normally when you just have a sum of limits, you can cancel out like that?
Well, if the limits existed, I could cancel, but they don't exist, so I can't very well say, infinity plus 1 is infinity. I mean, this is just infinity. I can't split off a finite piece from it.
But if there's something in both of those and one, you can cancel.
Yeah, if this had gone to 0 and that had gone to 0,
Right.
then I could have been canceling things, and yeah.
So, what would be the final answer?
Final answer is infinity.
Okay.
Yeah. So the integral in total diverges. Yeah.
So even though it's bounded on both sides, it's still...
But it's unbounded in the middle is the thing, and that got it. Okay, guys. So tomorrow I will talk to you about comparison theorems, which are very, very nice, very useful because they allow us to avoid integrating stuff we don't want to integrate. And we'll do a couple of standard examples that are important for our future reference in chapter 12. So anyway, we'll try to wrap up chapter 11 tomorrow. Thanks, guys.